Once we have a basic graph structure in place, it really becomes essential to search that graph structure. The graph structure itself really is just a model for representing the network of data items. It doesn't actually give us much information on its own. I mean, very basic statistics, nothing terribly interesting. So the navigation through a graph allows us to collect significant interesting data, such as are two vertices in the graph connected? So does this street in some way connect to this other street, or does this person have some relationship with this other person, or whatever that data might suggest? It also helps us discover pathways. So if there is connections between two streets, how do I get there? What streets do I turn on? How far do I go? Or again, if I want to meet someone, who do I ask to get a friend of a friend to get there? It also helps us to detail that network and detail the association between the network. How dense is the network? Are there separate subnetworks inside of there? There's all sorts of questions we can answer through searching graphs. Now, again, the search is a little bit different. There's a functionality to search, but the functionality to search leads to the data, and so the search itself is an artifact. So as we if we have a map, which is kind of a graph, and we want to get directions on a map, the directions become data separate from the map. It uses the map, it talks about the map, it informs about the map, but it's still a separate artifact, if you will, on its own. It's a separate list of data and can be interacted with even after the map is done. Now, there's some risks inside of there that the map could change. Roads could close, or you know, other condition, new roads could emerge that might change the answer. So you need to be aware of that when you do a search. That the search is not necessarily all the time updated with any changes to the graph that's out there. But it does give us a nice ability to do that search and not have to continually go through the heavyweight map afterwards. So in general, the search strategy of everything we'll talk about is pretty straightforward and uses a similar approach. So if you kind of think of our graph as this little elephant here, and it's a paint by numbers elephant, if you will. Every single vertice has its own identifier. And our search strategy is to go from one vertex to the next and mark it as being visited, and then use that information to simplify and not repeat redundant searches. So every one of the search strategies we'll talk about today, and it might be everyone everywhere, uses this idea of I have this big array of essentially Booleans. Did I visit this or not? And that kind of drives out the search. Now, there's other algorithms and other strategies and other data we'll capture beyond that, but this is a really important idea. It's just simply I say I start someplace. In this case, I'm starting on vertex number 2, and I say, okay, well, let's go to vertex number 2's adjacent nodes. Maybe 0 is one of them, and I check that off. And maybe 5 is one of them, I check that off. And then maybe 6 is either connected to 2 or it's connected to 0 and 5 or whatever it is. And so I'm just kind of checking them off as I go. All right, so that foundation sets us the type of data that we're going to navigate through the search. Now, there's many different ways we can then approach it from there. We can do it iteratively, we can do it recursively, we can answer different questions based off of our algorithm. So the first one we'll dive in is the recursive search, which is a depth-first search. So if we were thinking of it as like this maze, we're essentially trying to get either from the center of the maze out or into the center of the maze, if you will. We're going to go as far as we can inside of here. We're not exploring all the options to the left or the right. We just keep heading towards the center, if you will. So at a high level, just kind of in some pseudocode here, when we do a depth-first search of a graph, we pick some place on the graph to start with. So a graph is a massive network of things. We don't really try and do across everything for the most part. We're not saying give me directions from every shop in town to every other shop in town. I'm going from my destination to some destination or set of destinations. So we basically pick some place, and then we're going to do this recursive search. And so the recursive search says, okay, I've got this graph, and I've got this starting vertice. So this vertex where I'm just going to start. And so I start that wherever I'm starting, I mark that vertex as being visited. And then if I'm counting how many connected vertices are in this graph, I increment that count by 1. And then for each of the adjacent vertices, I check, have I visited that vertex already? And if not, then I search that vertex. So again, I go down and down and down. I don't, so if you think of it this way, if you are walking up your family tree, if you start down your mom's side of the family tree until you reach the dead end of the origin of the family tree, or you can't get any more information, you don't look at all at your father's side of the family tree. You are really just diving straight into one side and ignoring the other side. So let's take a look at that in action. So we have this network of the vertices inside of here, this graph, and so now I've labeled them A through J, but the same concept is in play. They could be 0, 1, 2, 3, 4, 5. I just want to align to the letters that are out here. Um, so I start at B in this case. So I mark B as being visited. And so then from B, I'm going to say, okay, well, let's take the first adjacent, which is now A, and I mark that as visited. All right, and then from A, I'm going to take its first vertex, which in this case is I. It doesn't have to be E. There's no ordering or sorting. It's whichever one, perhaps got added first to the list. So then I gets added inside of there, and that gets marked. And then I follow that to E, and E gets marked, and then well, A is already marked, so I don't have to do another search there. So I go to F, and F gets marked, and then I go to D, and D gets marked, and then I go to G, and it's the next one over. G gets marked, and then finally I get back to B, which is already marked, and then recursively I walk up the chain. And so we can see here, by investigating the query about starting with the B as the starting vertex, I end up with this count of 1, 2, 3, 4, 5, 6, 7 vertices in this graph. There's 3 others in the subgraph, I should say. There's 3 others that are in the full graph, but they didn't get counted here. They weren't marked. And so now, if I'm have this search results and I want to know, well, if any particular vertex is connected to B, I have this record of booleans just to say, well, hey, is E connected to B? Yes. Is D connected to B? Yes. Is C connected to B? No, it's not. There's no check mark here. It's false. So the depth first is a really, really great and effective way to be able to walk quickly through the entire network and see what's connected. And there's other things we can do with depth first, but this strategy again is very simple code, very simple algorithm, very simple code. So that's one of the ones you will code. Again, this algorithm is not. I'm not putting this here for you to reverse engineer and invent this yourself. The algorithm's out there online. It's in the book. You can get it from a number of places. So feel free to refer to that. But this is kind of the approach if you're trying to trace your code that you should understand and be seeing. So you might want to try that one now, but there's other searches that you might choose instead. So we'll talk about some of those next.